Hi, everyone. So it's really nice to be here today to talk about the formal proof of the fifth Busy Beaver value. And to jump right into it, here's a Turing machine. So we have a bi-infinite tape. At start, we have zeros in all cells. And we are just going to do what this machine tells us to do. So here in state A, it tells us to write a 1, go to the right, and then read our next instruction in state B. So it's what we're going to do. And clicking this button, we get some Turing machine operation done. But at some point, we can wonder, will we ever enter this undefined operation over there, which would result in the machine halting? Here, it would happen if we ever read the 0 in state E. And here, patience is our friend because 47,176,870 steps later, happy to have said it in the talk, the machine halts. So here's what it looks like if we zoom out. That's a space-time diagram. So each row of this image, it's a successive state, and I've used the pixel white if I had a 1 and black if it was a 0. And we see this kind of pattern of sort of bells that nest into each other, but at the end manage to enter this edge case where it halts. A natural question when we've seen that is, okay, but could you do any better? Like, can I work with a machine that would achieve a bigger number? And that was exactly the question asked by Tibor Rado in 1962 when he introduced the Busy Beaver number, which is the maximum number of steps that a halting two-symbol Turing machine with end states can do when you start from the all 0 memory tape. My PhD supervisor, Damian Woods, used to say that it's maximum algorithmic bang for your buck. So it's like what is the most you can do when you are constrained in the size of your program. This isn't computable, yes, because you could solve Turing's halting problem otherwise. However, we cannot know, we don't have an algorithm to know all values, but we can certainly try to know some values. And here's the history of it. Until recently, we knew 4 values. The latest one in 1983, due to Ellen Brady. And what it means is that if a Turing machine with 4 states runs for more than 107 steps, then you know it will never halt. In that way, we can understand that the Busy Beaver number is sort of an oracle for the halting problem of the class of machine it corresponds to. And in 1989, Marxen and Buntrock, two German computer scientists, found the machine that I started the talk with. And for many years, there were no better machine found. So eventually, Scott Aronson conjectured, well, you cannot do any better. And it makes sense to think that this is the value. However, of course, we didn't have a proof. And so in 2022, during my PhD, I started an online collaborative research project called the Busy Beaver Challenge, BB Challenge for short, where the goal was to collaboratively solve the conjecture. It consists of a website. So this page here where you can, it's a bit like a Pokédex where you can see all the machines and like see what they look like. A Discord server where most of the talks about research happen. A wiki, which is helpful for long-term retention of knowledge that is created in the chat and other, and sort of a galaxy of GitHub repositories that are each contributor would have their own GitHub repository and share the work they do. So there was, I think it's interesting to mention that there was no management of research. It was sort of entropically driven, people making discoveries and just working on what they wanted to work to make the problem go further. And today we have about 1,000 people on our Discord server, and I'd say around 50 people that are really active and that work on this problem day and night. So how do you prove that BB5 is equal to this number? Well, first you enumerate all 5-state Turing machines. You encounter a first problem here because there are a lot, like 10,000 billion. But if you do things in a sort of a nice way, you end up with only 181 million. That's the number of machines that are enumerated by the coq proof. Then you craft some automated proof strategies. We call that deciders, so programs that take as input a Turing machine, and we either say, well, if it holds, it doesn't hold, or I don't know. In which case, if it doesn't know, you're going to try another decider. the final proof has about 6 deciders that are used, but I'd say that about 20 or more have been developed by people working on the problem throughout the years. And then you might be left with some machines that were not captured by those automated proof strategies, and you have no choice than prove them by hand. In the case of BB5, there were 13 such machines, and we'll talk about them a bit later. So deciding the undecidable, well, it's impossible. There's no universal decider. But you could ask, okay, well, how impossible? And well, this is impossible in the sense that any pi1 statement can be encoded as the halting problem or the non-halting problem of a Turing machine. I mean by that, a good example to understand this statement is Goldbach's conjecture. So one of the longest standing problems in mathematics says that any even number can be written as a sum of 2 primes. And how am I going to check that with a Turing machine? I'm going to enumerate every even number, and then all primes below those numbers, test all the sums. And if I don't find a sum that works, I will halt. I will have found a counterexample to the conjecture. And so because Riemann hypothesis can be made into a pi1 statement, you can build a Turing machine. And then ultimately, well, the consistency of a set of axioms, it's a pi1 statement because you can just enumerate all proofs until you find a proof of 0 equals 1, for instance. And this has been done, and we see that quickly with relatively big small numbers, we get into very hard territory.
This number, this
yeah.
number 748 was lowered to 700 point with.
Yes, yes. I'm sorry. I should add here. There's a beautiful master thesis or undergrad thesis that was written on that, and yeah. And similarly, this number here used to be 27, but people that worked on the lean formalization of the result reduced this to 25. So, okay, it's impossible, but let's do it anyway. And the hope that we have in the back of our mind is that, okay, but 5-state Turing machine cannot be that hard. But in my mind, I would have loved for them to be really hard because it would have meant that we would have found like the smallest open problem in mathematics encoded in just 5 states of a Turing machine. So that was my secret hope, and it did not happen. But since 2022, contributors produced dozens of those deciders, so strategies to solve sub-problems of the halting problem in any language you can think of. And bbchallenge was not proof assistant centric, meaning that when I started the challenge, I thought it would be really hard to do. I had this a phrase on the website, like, yeah, it would be nice if you do it, but okay, it's impossible, so it's okay if you don't do it. And instead, what were we doing? We were asking a very strict validation process, like any decider that was written by someone had to be matched by an independent implementation. And we asked a latex proof for lack of better alternative. But the power of collaboration really exceeded my non-expectation on this because as soon as 2022, a first contributor, Nathan Fenner, started writing deciders in Daphne, which is one program for writing formal proofs about programs. And very quickly after, Maya, who is here in the room, and who will happily talk to you about the details of this, started introducing the community to Coq, where she wrote some deciders, and the goal was to extract them to OCaml for performance and run them in OCaml ultimately. And with the project Busy Coq that she did, there were 12 out of the 13 machines that we had to prove by hand were done as part of that project. In 2024, however, using Coq, an anonymous contributor called MXDYS joined the project and showed that they had translated, improved and created many new deciders, implemented the enumeration of all the Turing machines. So I want to stress this point because it's what I personally thought was not really feasible, not scalable in a proof assistant, was this algorithm that enumerates the 180 million proofs. I was very, machines, I was very skeptical as it being feasible. And so no, they proved us wrong because they did it in Coq. And they proved the last machine that was standing. There was one particularly hard machine, and the proof is about 10,000 lines in code. So that way, MXDYS provided the proof of BB5 equals BB5 in COP. So I want also to stress that the difficult part is not to write the decider algorithm in Coq, it's to prove that it's correct, of course. And similarly, you need to make some proofs that your enumeration strategy is sufficient, that, okay, I'm not enumerating the 10,000 billion machines, but the subset I'm enumerating is enough. Coq BB5, so it was released in 2024, and it encompasses 6 deciders here. And the folder structure of the repository really follows this terminology where we have one file per decider. All of these deciders have the nice properties that they fit in a framework where basically you are reducing the language that the machine is outputting into a regular language. So in one way that I won't go into details, all 5-state Turing machines are sort of reducible to regular languages, but about 17 plus 13, for which there are no regular proofs. Here we use weighted finite automaton, which are an extension of finite automata to non-irregularity. It's also a nice separation with BB4, because for BB4, all machines are regular. So you have this nice regularity argument that separates 4 states from 5-state machines. Initially, it compiled in 13 hours, and Yannick Forster, also present in this room, improved that to about 45 minutes. And actually, it could be improved arbitrarily because the proof has a tree structure, and so you can cut your tree in different files and compile those files in parallel. We have done that to a certain extent by hand, which brings it down to 45 minutes, but you could continue to do that arbitrarily far. Also, switching to cognitive engine allowed the code to go much faster. Finally, we did an OCaml extraction of the proof to make the proof non-silent, because by default, the proof doesn't say anything. It says, okay, we've proven the result, but what we would like to see is a CSV list of all the machines and do they halt or not, and for what reason. So we've done that, and we've released this list that tells you for each 5-state machine the reason why it halts or doesn't halt. So here's a statement of the theorem in Coq. I want to highlight that all the definitions and the theorem statement with comments, it only ends up in a file that's relatively small and quite transparent. You don't need to be an expert in Coq. I was certainly not an expert in Coq to understand it. And here, so the theorem about the value, it's saying, well, for all Turing machines and halting time, if you halt at that time, then the halt time is less than BB5. And if you don't halt, and otherwise you do not halt. Similarly, the theorem is broken in two. You have the lower bound, that's very easy. You just show Coq the BB5 champion that we started the talk with. You say, hey, this machine halts in 47 million steps. So Coq knows that it's a lower bound on the value of BB5. And then you have the upper bound that's tricky, where you need to run the enumeration, call all the deciders, and solve the remaining cases that were not solved. The proof uses one axiom that has been discussed this morning, and I assume you are familiar with, so functional extensionality. And apparently, the proof could be refactored not to use it, but it will make the proof a lot more ugly in some way. So in summary, here's the landscape of small Busy Beaver value after our work. So what I didn't tell you is that you can naturally extend the definition of Busy Beaver to more than 2 symbols, and that there were some results already known in the literature. It was known that BB2, 3, so 2 states, but 3 symbols was equal to 38. What I didn't tell you is that MXDYS, on top of proving BB5, also proved an unknown value, which was BB2, 4, so 2 states and 4 symbols. The thing that's interesting is that, well, first, the bands that we have in all neighboring classes are quite big. For instance, the current 6-state champion halts after 10 tetration 15 steps, so 10, 10, 10, 10, 10 power 10, power 10, power 10, power 10 times. And here you have this new band that was discovered recently. No, sorry, my slides are not updated. There is a band that is bigger than this, I believe that was, but this is already huge. The thing that's actually funny is that there are only 6 machines left in that class, BB33. And there's one that we really think it halts, we just cannot show it. And if it halts, it will really break this very small 10 to the 17 bound because we have simulated it for a huge amount of stuff. The orange on this graph, it's about what we call cryptids. So Turing machines for which we know or believe that's problem to solve is extremely hard. So there is this 6-state Turing machine that was found by MXDYS and Rachel Hunter that reduces to this collatz-like problem. So you iterate this collatz-like map, which was studied in the literature before, by the way. And you start from 8 and you ask if you will ever see twice as many odd terms as even ones. If you're familiar with collatz or if you have heard of it, it's a very hard type of problem where everything looks random. So this problem looks very hard, hence knowing if this machine halts looks very hard. And in all those neighboring classes, we have examples of such machines that reduce to something really, really crazily hard. We also have broad-cock proof for the result that was known before in the literature, just because that's probably the only result we'll ever be able to add to our. So about future work, although it seems hopeless, the next values, a lot of work has been done. You see, there are only about 4,000 machines left to solve BB6. A lot of new deciders have been developed, and over 33 billion machines you need to study this time instead of 180 million. And it still is runnable in COP, and about 4,000 machines are left. 80 machines in that class here, BB25, and 6 machines in this class with the conundrum of a machine that we think it halts, but we have a probabilistic model that says there's 100% probability that it halts, but we cannot prove that it halts. There's still open question about 5-state machines, though. I didn't get a chance to talk a lot about them, but they have a wide variety of behavior, from relatively boring ping-pong kind of behavior to counting in many different bases, base 2, base 3, base 3.5, and you name it. And here some fractal self-repeating patterns or other weird things. And in particular, I mentioned that we had 13 very hard machines to solve. And in that set of 13 sporadic machines, as we call them, there are 3 that really took a lot of effort to prove. This one enters the cycle, but after 10 to the 51 steps. So with 5-state Turing machine, you're able to encode the idea of 10 to the 51, which is a lot bigger than 47 million already. And the period of the behavior is about 10 to the 9. Here you have a machine that implements a double Fibonacci counter. So there is a theorem that says that you can count in base Fibonacci, meaning that any number you can write as the sum of 2 Fibonacci numbers. Here the machine does that, but it does it twice. It partitions on the right side of the tape and the left side of the tape and does it a bit slightly different. And it would halt if only if the 2 counters would ever get out of sync, and they don't. And finally, the last boss of the 5-state machine, this machine called Skelet 17. And by the way, this name Skelet, it's in reference to the person that first found those machines in 2003, who went under nickname Skelet, whose name is Georgi Georgiev. And this machine implements gray code, but under like 6 or more layers of obfuscation, meaning that, yes, it took a lot of work and a separate preprint to just prove the behavior of this machine. So I would like to thank all the people whose contribution helped solve this problem. Special thanks to Maya for all her work in the challenge, but also for some of size that I stole from her. We always welcome new contributors. And I would also like to say that the first draft of our paper is online, and we are in a phase where we welcome feedback from anyone. And so especially people talented in proof assistance, it would be really nice to have your opinion. So all the links that I shared in this talk are under this QR code. You will get to a page with all of them. And in particular, also a nice piece that Quanta Magazine wrote about us. So thank you very much.